Hello, folks, and today we're going to have a look at the nuclear radiation questions from the National 5 Physics paper in 2017. These are questions 5 through to 7, and the first one is actually an open-ended question. It says, alpha, beta, and gamma are types of nuclear radiation which have a range of properties and effects. Using your knowledge of physics, comment on the similarities and/or differences between these types of nuclear radiation. So there's lots of different things you can say here. Actually, the difficulty of this question is knowing when to stop rather than knowing what to write. We could tackle this looking at size, because alpha, beta, and gamma, well, alpha are made of large particles. They are 2 protons and 2 neutrons, as we can see in the little animation there. So they have a large mass, whereas beta is a high energy electron emitted from the nucleus. So it's got small mass. And gamma is a piece of high frequency electromagnetic radiation. So it has no mass. Or we could have a look at this in terms of their electrical charge, because alpha is a particle which has a charge of 2+, 2 protons. Beta has a charge of -1 because it's an electron. And gamma, it doesn't have any charge. We could think in terms of its penetration properties. So alpha, because it is the largest particle, is the least penetrating. So it will be blocked by a single sheet of paper. Beta is a little bit more penetrating. It will pass through paper, but will be absorbed by a few millimeters of aluminium, whereas gamma will pass through most things and will only be absorbed even partially by a few centimeters of lead. So gamma is the most penetrating and only absorbed by several centimeters of lead. Beta is less penetrating and is absorbed by a few millimeters of aluminium or a few meters of air. And alpha is the least penetrating and is absorbed by a sheet of paper or a few centimeters of air. We could also talk about the ionization density of these types of radiation and talk about the fact that alpha has the highest ionization density because of its large mass and its larger charge. Beta has a lower ionization density because it has a lower mass and less charge. And gamma has the lowest ionization density because it has no mass and no charge. Moving on to question number 6 now. A technician uses the apparatus shown to investigate the effects of shielding gamma radiation with lead. Gamma radiation passing through a lead absorber is detected by a Geiger-Müller tube. The count rate is displayed on the rate meter. The count rates for a range of different thicknesses of lead absorber are recorded. Using these results, the technician produces a graph of corrected count rate against thickness of lead absorber, as shown. A. State what additional measurement the technician must have made in order to determine the corrected count rate. So the corrected count rate is the count rate that is being picked up from the detector minus background radiation. So the corrected count rate is only taking into account the radiation that is coming from the source we're investigating and not the wider atmosphere. So they would need to know, in order to work out what the corrected count rate is, they would need to know the background count rate. The half-value thickness of a material is the thickness of material required to reduce the corrected count rate from a source by half. Using the graph, determine the half-value thickness of lead for this source of gamma radiation. So what we need to do is notice here that the initial count rate with no lead in place is 680 counts per minute. Therefore, to drop it to half of the count rate, that is a drop from 680 down to 340 counts per minute. Now we need to have a look at our graph and find out where does 340 lie on that graph. So we read across from the corrected count rate of 340 and then read down to the thickness of lead absorber required, and we find that it is 4.4 millimeters of lead required. Part 2. Determine the thickness of lead required to reduce the corrected count rate to 1/8 of its initial value. Well, we've just discovered that to reduce the count rate to 1/2 of its original value, we needed 4.4 millimeters. So to reduce its count rate to 1/4 of that much, we'd need twice 4.4 millimeters. Therefore, to reduce it by half again, to make 1/8, because 1/8 is half of 1/4, we would need 3 half-value thicknesses worth. So 3 times 4.4 millimeters, which is 13.2 millimeters. The technician suggests repeating the experiment with aluminium absorbers instead of lead absorbers. Predict how the half-value thickness of aluminium would compare to the half-value thickness of lead for this source. Well, we know from talking about the absorption properties of different types of radiation that aluminium is a less effective absorber, and therefore the half-value thickness of aluminium will have to be much greater, mainly because aluminium is less dense than lead, so it doesn't stop radiation as well. What this means is you would need a thicker piece of aluminium to reduce the count rate by the same amount. Part C. When working with the radioactive source, the technician is exposed to an equivalent dose rate of 2.5 times 10 to the power of minus 6 sieverts per hour. The annual equivalent dose limit for the technician is 20 millisieverts. Calculate the maximum number of hours the technician may work with this source without exceeding this limit. Well, what do we know? Well, we know the equivalent dose rate and we know the equivalent dose limit. So we have this formula, H dot equals H over T. So equivalent dose rate is equivalent dose over time. We want to work out time, so we put those numbers into our formula, do a little bit of rearranging, and we get 20 millisieverts divided by 2.5 times 10 to the power of minus 6 sieverts per hour, and we get a time of 8,000 hours. That's about 330 days, if you're interested, which means it's unlikely the worker will be spending 24 hours a day, 7 days a week for nearly a whole year with this source. So therefore, it's not going to exceed their dose limit. Number 7, nuclear reactions are used to generate electrical energy in a nuclear power station. The fuel for the power station is in the form of pellets containing uranium-235. A fuel pellet has an activity of 80 kilobecquerels. State what is meant by an activity of 80 kilobecquerels. So, activity is the number of decays per unit of time. A becquerel is 1 decay per second. So 80 kilobecquerels means that 80,000 nuclei are decaying every second. Part B. In a nuclear reaction, a uranium-235 nucleus is split by a neutron to produce 2 smaller nuclei, 3 neutrons, and energy. Explain how a single reaction can lead to the continuous generation of energy. Well, what happens is one single neutron causes 1 uranium nuclei to fissure, to break apart. That releases 3 further neutrons. These 3 further neutrons can then collide with 3 further uranium nuclei, which causes them to break apart, releasing 3 further neutrons each, which then go on to collide with 3 further uranium nuclei each. And so the reaction spins outwards and continues to self-propel itself. So I would write neutrons released in a fission reaction go on to collide with further uranium nuclei, causing further fission reactions. This then releases more neutrons and the process repeats. Part 2. One nuclear reaction releases 3.2 times 10 to the power of minus 11 joules. In the reactor, 3 times 10 to the power of 21 reactions occur each minute. Determine the maximum power output of the reactor. So, first of all, one reaction releases 3.2 times 10 to minus 11 joules. But there are 3 times 10 to the power of 21 reactions occurring every minute. So therefore, we can find out the energy released per minute. That's 3.2 times 10 to the power minus 11 joules per reaction multiplied by 3 times 10 to the power of 21 reactions. And that gives us an energy of 9.6 times 10 to the power of 10 joules per minute. To turn that energy into power, we use the formula power equals energy over time. So it's that number divided by 60 seconds for 1 minute, which is 1.6 times 10 to the power of 9 watts. That's 1.6 gigawatts. C. The nuclear reaction produces waste that emits nuclear radiation. State a use of nuclear radiation. Well, there are a whole range of different things you could use here. Cancer treatments, using radiation to kill cancer cells. Sterilizing instruments, using radiation to kill bacteria on medical instruments. Radioactive tracers, injecting somebody with a radioactive isotope, which then emits radiation that can be detected outside the body and be used to trace the body systems, the circulatory system or the digestive system or whatever. Smoke detectors, where a small alpha source is used, which ionizes the air and allows a little current to flow, but the ionization is blocked when the smoke detector absorbs smoke. Pipeline leak or blockage checking, where radiation is allowed to pass down a pipeline, and by tracing it on the surface, we're able to see if the pipeline is leaking or if there is a blockage. Measuring the thickness of foil or paper, so using a radiation source and a detector on the other side and allowing the radiation to pass through the foil or the paper. Measuring how much radiation passes through allows us to see how much radiation is being absorbed. The thicker the piece of foil or the thicker piece of paper, the less radiation that will be absorbed. So we can use that as a way of checking the thickness of foil and paper at the point of manufacture. And a whole range of other things. And folks, that's the end of the radiation questions from the 2017 paper. I hope that was useful, and we'll have a look at some of the other questions another time.